And we are recording. Okay, so partial fractions, just a new technique of integration. It's different from all the other ones we've done. It doesn't quite build on any of those, but of course, just like we saw with trig substitutions, sometimes at the end of a problem, you have to then use a U sub, or in these cases, we might have to use a trig sub. So partial fractions. So what are partial fractions? We are going to use these for integrating rational functions. And specifically, essentially what it does is it undoes a common denominator. So it's a common technique, right? Whenever we're adding rational functions, adding or subtracting rational functions, you find a common denominator, then you stick them together, and then you often have to do some sort of algebra to simplify them. Well, now in Calc 2, when we see this, in some sense, we're seeing one rational function, and what we want to do is split it into a sum of simpler rational functions. So it's going to split rational function into a sum of simpler rational functions. And then with these simpler rational functions, we can then integrate those, or possibly do at least an easier technique, a U sub, to finish off the integrals. Okay, so one thing to note before we get going, fact. This is the fundamental theorem of algebra. And it basically says that any polynomial can be factored. And I guess you should say any polynomial with real coefficients. Of course, this is Calc 2. Everything we're doing is over the real numbers. So any polynomial with real coefficients can be factored into irreducible factors of degree 1 or 2. So essentially, you can always factor a polynomial into linear factors or quadratic factors. Anything of degree 3 or higher, you can always factor in some way, shape, or form. Of course, doing so is a little difficult. I don't know how much you guys remember from pre-calc, but once we get polynomials of degree 3 and 4 and beyond, it's really hard to factor those without fancy tricks like this rational root theorem and things like that. Those get really lengthy, and so we're not going to actually emphasize that too much. Most of the factors, the polynomials that you'll see, are degrees 2 and 3, and if it's beyond that, usually we'll already have them in factored form. So let's take a look. Let's just start with an example of how this is going to work. And I want to kind of do an example and then sort of consequently on the right and like dually write out the steps that I'm doing, because essentially all these problems are going to be the same. So our example, we want to integrate 5x minus 4 over 2x squared plus x minus 1 dx. Let's see, so is that on the screen? Move it down a little bit, sorry. So there's our function. And so our first step is to factor the denominator. So we've got 2x squared plus x minus 1. Hopefully you guys remember how to factor these. You guys are Calc 2 students, so you guys are pretty good with all this kind of stuff. If you remember, my pre-calc students like to do this factoring by grouping, essentially is what it says. So of course you take this coefficient, and multiply them, and we just get 2. And then we're looking for factors of 2 that will add or subtract to get the 1. So of course it's going to be 2 and negative 1. And so what we want to do is write this guy as, we can write it as 2x squared plus 2x minus x minus 1. So all I did was kind of split this x and wrote this middle term x as positive 2x minus x. And the reason I did that was because of the 2 factors there. We made those 2 factors kind of work nicely with each other. And so we can group these 2 terms and then the last 2 terms, and we can factor this as, 2x times x plus 1 minus x plus 1. So of course, these 2 guys, all I did was factor out the negative 1 from both of them. These 2 guys, I factored out a 2x from each of those. Once we have it like that, we see that it factors as 2x minus 1, x plus 1. So we've got 5x minus 4 over 2x minus 1, x plus 1 dx. So first step, factoring the denominator. Step 2 is we want to write a sum of rational functions with essentially the factors of denominator and the numerator are generic polynomials.
Now, I'm not saying he wrote a child orgy in his book, but he wrote a child orgy.
With degree 1 less than the denominator. Might be a little confusing is what I mean by this. So let's just do it, and then it'll kind of make sense. It's kind of a weird step to write out as a basic, step. There's kind of a lot going in there in words, at least. So all it means is we've got our factors of the denominator. So in some sense, all the first work of these types of problems, we're going to ignore the integral. We really got to work with the function and just manipulate it into something nice that we can actually integrate. So what we're going to do is we want 5x minus 4 over 2x minus 1, x plus 1, equal to, we're going to write it as a sum of 2 polynomials where the denominators are split. So we're essentially splitting the 2 factors. What goes in the numerator? Well, so we write a generic polynomial with generic coefficients, and it'll be 1 less degree than the degree of the denominator. So in these two cases, we have a degree 1 polynomial. So that means the numerator just needs to be a degree 0 polynomial, which is just a constant. So we'll label the first constant as a. Over here, again, a degree 0 polynomial should go in the numerator. A different constant, we'll call that b. And so our theory of partial fractions says, well, if I start with a sum of these two rational functions, I can find coefficients such that if I were to find a common denominator of these two guys and add them, I should be able to get back to the original function I started. So step 3 is going to be solve for the coefficients. And there's two ways to do this. There's the proper way, and then there's a trick. And actually, I would prefer you guys, you want to actually do both. The trick makes things a lot easier, but you cannot neglect the proper way to do this. So the proper way to do this is to simply find a common denominator. And get a system of equations. The trick, which we'll do in the next problem, but I want to write it here, is to check nice values of x. So let's see what I mean by this. I want this equation to be true. So if I were to find a common denominator for this right side to try to get back here, well, I need to multiply this a term, so to speak, a times x plus 1 over 2x minus 1, x plus 1. So I just multiplied it by x plus 1 over itself. And likewise for the b term, we have to multiply by the other denominator over itself. So 2x minus 1 over 2x minus 1. And let me move that up, make sure we're still on the video. Okay, so I should have that this rational function equals this rational function. And when two rational functions are equal, if the denominators are equal, that means the numerators are equal. So that's really what we're looking for, is that we have this equation for our numerators will be this. And now we can solve for a and b. We've got to do a little bit of work first, but we can just solve this as a basic polynomial equation. So how do we solve it? The proper way is to expand everything out. So we will have ax plus 1 plus 2b x minus b. Combine your like terms, and I guess I should say combine the coefficients for powers of x. So write it as like a polynomial. On the left, we have something times x minus a constant. So we have ax plus 2bx is going to be a plus 2b is the coefficient for x, and our constant term is 1 minus b. You guys still seeing that? Yeah, looks like I'm still on the screen.
When you distribute the a into x plus 1, why isn't it ax plus a?
Ah, it is. Thank you for catching.
Okay.
Ax plus a, and so that guy's an a there.
One more question.
Yeah.
On the left side of the equation, did you move the denominator over to the right side? Is that why that disappeared?
You mean like take this denominator and multiply it over?
Yeah, or is it just
You
how
can
you
kind
do
of
it?
think of it like that. Really, it's the fact that if I have two rational functions that are equal, if the denominators are equal, we just set the numerator
Thank you.
equal
Thank
as
you.
well.
I see.
So
Yeah.
it's essentially the same thing, yeah. Okay, good. So thank you for catching that mistake there. And then once we have two polynomials that are equal, this just means that the coefficients for corresponding powers of x have to be equal. So what this tells me is that my coefficient for x has to be the same. So we'll get the equation 5 equals a plus 2b. And likewise, the constant terms have to be the same. So negative 4 equals a minus b. So this is our kind of common denominator and then system of linear equations, or system of equations. Sometimes they're not linear. Actually, I think most of the time they are, though, since our constants are always constants. Okay, so how do we solve that? You can do any sort of system of linear equations trick. Unfortunately, we don't teach systems of linear equations in calculus or in pre-calc anymore. So really start with whichever one's simpler. You can always just solve for one variable and substitute it in the other. So let's go ahead and start with the right side. Add the b over. So it's going to be b minus 4 equals a. We're going to plug now this in for a. So we get 5 is equal to b minus 4 plus 2b. And so we get 5 is equal to 3b minus 4. I add the 4 over, we get 9 is equal to 3b, and b is equal to 3. You guys still seeing that? Yeah. So we solve for our b. And then, of course, I can solve for a. So that's the bulk of the work right there. It's just, this is the partial fractions part, is splitting a rational function into sort of its partial fractions, its partial factors with different denominators or simpler denominators. Okay, so let's rewrite that. What do we have? We just showed that 5x minus 4, let me see, am I on screen? Yeah, there we go. Over 2x squared plus x minus 1. We showed that that can factor into a over 2x minus 1 plus b over x plus 1. And we found our specific factors. Our a is negative 1. And our b was 3. So our original integral we can write like that with these new, oops, it's a minus, with these new factors. So that's going to equal the integral of negative 1 over 2x minus 1 plus 3 over x plus 1 dx. Once you found your coefficients, then the last step is really just to integrate. And of course, you might need another technique. Sometimes U sub or trig sub will come into play at this point. In this case, you don't really need either. You could, right? If you're still having a little bit of trouble of integrating something like this, We could always do a u sub for this guy. U is equal to 2x minus 1. Likewise, a u sub for this guy. Split this into two integrals. I do want to challenge you guys with these kind of u subs. Again, I mentioned this either yesterday or Wednesday of like, this is really a constant like 1 over a linear factor. So it's just like 1 over x. And if we're integrating 1 over x, we should get natural log. So when I integrate this guy, we're going to get the -1 is our constant. So it's going to be -1 natural log of 2x minus 1. Whoops, let's keep the absolute values in there. But of course, when I take a derivative of this, we'll have a chain rule. We'll have another factor of 2. So we need to divide by that factor of 2 to undo that. It's kind of it's really just doing a u sub just by thinking it through. I could do a u is equal to 2x minus 1. Then my du is 2dx. And so when I solve for that dx, that's where that factor of 1/2 will come from. Likewise for this guy, we'll have plus 3 natural log of absolute value of x plus 1. And because the derivative of x plus 1 is just 1, I don't have to worry about any extra factors that are going to float around that we have to deal with. So check that. You can always, take the derivative of these guys now in your head just to check to make sure you're getting back to what you had. And then, of course, we got a plus c. Any questions on that?
Just need a sec to write it down.
Sure.
So those are absolute values on the ln, the natural log?
Yeah, absolute values.
Gotta
here.
make sure we have absolute. All right.
Yeah. I'm not a big stickler for absolute values. Like if in a written problem, if you include it or not, it's not a big deal for me. I wouldn't take off points. If you're in Corey's class, I don't know. I would check with him how much he really cares about the absolute values. Really, as long as you understand how to integrate something like that and know that it's natural log, that's kind of what I'm looking for. All right, everyone all set? No more questions? Let's take a look at another example. This one will be a little bit easier, and we'll do some of the tricks that will simplify the system of equations part. Because system of equations, that one wasn't too bad since we only had 2, but as they get, with more variables, it gets harder. So I kind of want to progress all these problems with getting slightly harder each time, or at least with slightly new techniques. This one may not be much harder, but it's some of the new techniques. So let's give it definite bounds just for the sake of plugging some things in. And let's say we just have 1 over x squared minus 1 dx. So our first step is to factor. Hopefully everyone's comfortable with that. Difference of squares. So that's our step 1, factor. Our step 2 is to write it as a sum we split the factors of the denominator, and then the numerators are polynomials of degree 1 less than a denominator. So since these denominators are both linear factors, these are both constants. And I'll do a harder one after this where what happens when I don't have just constants on top. So that's our step 2. Our step 3 was then to solve for the coefficients. So we're always going to have an equation that looks like this. Essentially, whatever your numerators are, in order to sort of reverse engineer that, if we were to find a common denominator, I essentially need to multiply this guy by the opposite denominator over itself. And if we have extra factors, we also have to multiply by those. And we'll try to do an example here. So we'll have that plus b x minus 1, and the denominator will then be x minus 1, x plus 1. So I kind of just did a couple of steps there, right? If I split this sum over the numerator, we would get back here because this term would cancel and I'd have a over x minus 1. This term would be b over x plus 1 since those factors would cancel. And so what is our numerator equation when I equate this numerator and this numerator? We just get 1 is equal to a times x plus 1 plus b times x minus 1. And so let's do a trick now. I could distribute everything again, come up with a system of linear equations, and then solve. But the fact is that this equation has to hold for all values of x. So pick nice x's to solve. So if it holds for all values of x, let's say what happens when x is equal to minus 1? Why am I picking x equals minus 1? Because that will kill this term, right? I'll have negative 1 here. So if x equals minus 1, what's the equation say? So this was x equals minus 1 for that step. Can you guys still see that? Am I running off? There we go. And so this just says 1 is equal to negative 2b. So it kind of got rid of that a term for me nicely, and then I can just solve for b easily. B is negative 1/2. And I got to use a new piece of paper here. So let's rewrite out what we had. We had this equation. And we solved b is equal to minus 1/2. I could plug that in if we wanted to, or we could just check another nice value for x. Say x equal to 1. And so what do we get? The b term then goes away, and now I can solve for a easily. So a little bit quicker there. I don't have to set up a system of linear equations. It's a way of, I can kind of skip the distributing here and then refactoring, collecting common powers of x, and I can just kind of keep it like this, plug in some of these x values to simplify and get these a and b terms rather quickly. So let's go back to the original problem. We had 2 to 3, an integral of 1 over x squared minus 1, which we factored, and we had an x plus 1, x minus 1, and let me see. So let me pull that up again. Let's see if I can put this on the screen. This is a common mistake, and it's kind of just a brain flub. Just make sure that your coefficients correspond. So I kind of rewrote it and then accidentally wrote those kind of in a different order. So just remember that our a term was over the x minus 1. So on the x minus 1, we found a was 1/2. So I'm going to write it 1 and put the 2 in the denominator. And our b term was -1/2. So I'll put that there, the x. And then our last step is just to integrate. So we will have a -1/2. We'll have natural log of x plus 1 plus +1/2 natural log of x minus 1. And then we want to evaluate 2 to 3. So hopefully everyone's still with me there. Any questions? Nothing too complicated on those antiderivatives, hopefully. And then we evaluate. So what do we got? -1/2 natural log of absolute value of 3 plus 1, just 4, plus 1/2 natural log 3 minus 1 is 2, minus -1/2 natural log, plug in 2, so we'll have a 3 there. And then plus +1/2 natural log of 1. So all in all, what do we get? -1/2. Let's simplify. We can do it in steps here. I'll do it real quick. -1/2 natural log of 4. That one can be simplified. We'll do it in the next step. Natural log of 1. Everyone recognizes, hopefully, it's just 0. Distribute that minus, so we've got +1/2 natural log of 3. What is -1/2 natural log of 4? We can do negative natural log of 4 to the 1/2 plus 1/2 natural log of 2 plus 1/2 natural log of 3. And of course, the reason I did that was because we have this natural log of 2 here. And if I pull that exponent up, this is just negative natural log of 2 now, plus 1/2 natural log of 2, plus 1/2 natural log of 3. And then I can add those two. So we're just going to be at -1/2 natural log of 2 plus 1/2 natural log of 3. So just some algebra there at the end. Got to remember your natural log rules. Any questions on any of that? Everyone got it all written down?
Just give me one more second.
Sure.
Okay, I'm good.
Good. New page.
And can you explain one more time what happened to the negative natural log 2 in the front?
Yeah. Between this step here.
Yeah, and that step and the next step. What happened?
Yeah, so it's just -1 times natural log of 2 plus 1/2 natural log of 2. So really all I have it as -1 plus 1/2 times natural log of 2. I kind of just factored out the two coefficients. I kind of factored out this natural log of 2 from those two coefficients.
Okay, I see. Thank you.
Yep. Any other questions? Okay, so we've got about 40 minutes. So let's just try to get through some more examples and get a little bit harder every time. Okay, so the next one's going to look at is what's happening when we what happens if I don't have these linear factors in the denominator? So far, all of our denominators have been nice, and all the numerators that we have to solve for are just constants. So let's do, we've got the integral of 2x squared minus x plus 4 over x cubed plus 4x dx. Is that on the video? Let me move it down. There we go. So 2x squared minus x plus 4 divided by x cubed plus 4x. So when we factor the denominator, we really just factor out 1 power of x. So anytime we give you a cubic, right, it's not as nice as quadratics where we have all these fancy techniques. Cubics are kind of hard to factor unless you know, like, if it's a specific one that'll work with factoring by grouping, or otherwise it'll have like a power of x that is just kind of blaringly there that I know I can factor out. And once we factor out that power of x, the remaining term is a quadratic. But can we factor x squared plus 4? We can't. If it were x squared minus 4, it'd be a difference of squares, and I could keep factoring. But it's x squared plus 4. Can't factor it anymore. So this is an irreducible factor. That's a quadratic now. That's degree 2. So how do we set up our partial fractions equation? Well, the first factor is easy. It's just x, and our numerator is 1 less degree. So it's a constant. But the second factor, since it's degree 2, we need a generic polynomial on the top that is degree 1. So a generic linear equation. What's a generic linear equation? It should be something like mx plus b. I'm just going to keep using the alphabet in the order, so let's write it as bx plus c is what that numerator should be. Just a linear equation. And now our same goal, we got to solve for those coefficients. And of course, if I find a common denominator, we should have a times our other factor plus, and mind your parentheses with this guy because it's full factor, bx plus c times the quantity x, and this should equal 2x squared minus x plus 4. So I'm skipping a little bit of steps here. Really, all I did was find a common denominator, right? I would have to multiply this guy by x squared plus 4 over itself. And so I would have that a times the quantity x squared plus 4. This guy, I would have quantity bx plus c times x over x. So that's where the x goes. Of course, then the denominators would be x times x squared plus 4 under both of those. Kind of skipping that step just to save myself some writing. Likewise for you guys, like, this is good enough work. If you go from this step to this step, understand, you know, where that step came from. Should be enough work. You know, we as graders and instructors will know where this came from. Any questions? That's not too fast for you guys, is it? Okay. Okay, so what can we do here now? We want to use both of our techniques. That the trick with just checking specific x values helps us a lot. The problem is I can't pick a nice x value for this guy. So, right, I can't pick, you know, x is equal to -2, because if I square it, it'll be +2. I can't kill this factor in some sense. I can't pick any x values that would make this whole factor 0. So we can't really mess with that guy yet. But maybe if we pick some of these other guys, it'll help us, and then I can solve that guy easily without having to distribute and then compare the coefficients, get these linear equations, and solve it. So since this guy is just x, I can pick, say, x equals 0. What's that going to give me? On the left, we will just have 4. Then on the right, we'll have 0 plus 4. And then plus, well, we have this bx plus c, b times 0, I guess we should have, plus c. And of course, that's being multiplied by 0. And so that term, we kind of don't have to worry about. That 0 will kill it. And so we are left with 4 is equal to a. 4 is equal to 4a, excuse me. And then so a is equal to 1. So that saved us a little bit of work. Let's rewrite of what we have. Since a is just 1, this term is just x squared plus 4 plus bx plus c times x. And unfortunately, like we mentioned, there's no other nice x values I can pick. But at least maybe now I only have these, a system of equations that it's only going to involve 2 variables to solve for. So by getting rid of that one, the sort of more complicated method is not as complicated. So let's go ahead and now simplify our equation. I can subtract these 2 terms over. So I will have x squared minus x is equal to, and let's go ahead and distribute this x. So we will have bx squared plus cx. So I just subtracted x squared, subtracted 4, so the constants go away. And bx squared plus cx, of course, coming from distributing. And the nice thing now is, well, this is all common terms. There's no extra powers of x or x squared that I need to combine and factor to find different coefficients. And once I have 2 polynomials that are equal, that just tells me that the coefficients of x squared, so that's going to be a 1 there, right, should equal the coefficient of x squared over here, which gives me a nice b equals 1, nothing more to solve for there. And likewise for the linear coefficient, c should equal -1. So hopefully everyone kind of sees how, doing this trick when you can kind of helps simplify the subsequent steps and makes them a bit easier. And so now let's just go ahead and rewrite our original integral. What do we have? So we had integral 2x squared minus x plus 4 over x cubed plus 4x. And we have that is going to be equal to the integral of our a over x. So a was 1. So we'll have 1 over x plus b was 1. So it'll be 1x minus 1 over x squared plus 4 dx. And so now, because we had this quadratic factor, it's a little more complicated now to integrate this guy. The common things you'll see in a lot of natural logs in your final solutions of these guys. Of course, we've already seen a few in the previous 2 problems. This guy, of course, is going to integrate to a natural log. The other things you will see is sometimes you will see arctan, right? So remember, what's the derivative of arctan is 1 over x squared plus 1, or x squared plus a constant. If you did any more exercises with these trig integrals that we did yesterday, you'll see a lot of substitutions for that, with arctan. And then the other thing you'll see is just other rational functions. So here I have this x in the numerator. So an arctan is not going to work here, but we can do a u sub for this guy. So if I have u is equal to, what should our u be? I have a degree 2 polynomial on the bottom, degree 1. So if I let my u be x squared plus 4, my du is 2x dx. So in other words, 1/2 du is the x dx. And so what is this going to be? I'm going to go ahead and integrate this first term. Of course, we can split an integral over a sum and just integrate each of those separately. So we'll have natural log of x plus, now let's go ahead and make these substitutions. We will have, oh, hang on one second, I missed something. What did I miss, guys? What's not going to work out here?
The -1.
Yeah, the -1. Let me rewrite that. This is the perils of not using a chalkboard, right? I got to rewrite everything instead of erasing. So let's rewrite that. What did we have? We had our integral of 1 over x plus, we had x minus 1 over x squared plus 4 dx. And I kind of mentioned this on our first day, right, with our u subs. We cannot have these constants in our substitution. I can't like force a plus something in this u du expression. So we can't have that -1 and substitute out the differentials. So how do we deal with it? Well, we just split it. So we'll have 1 over x plus x over x squared plus 4 minus 1 over x squared plus 4. So now I can do a u substitution for this guy, which will work. And so when we do the integrals, we'll have natural log of x. Of course, I'm splitting all these integrals. I'll put my dx's in all those. Plus the integral, we need that 1/2 here. So we will have a 1/2, and now this is just 1 over u du minus, how do we do this integral? Do you guys want to see the steps for all that? Or can we do it kind of quickly? Let's write out the steps for this guy as well. So what's our substitution here? A u sub won't work for this guy, and so we need to use a trig sub. So what is our trig sub, right? We want to take advantage of the fact that tangent squared theta plus 1 equals secant squared theta. So this is our trig equation that takes a sum to just a single term. But, of course, I have this plus 4 here. So what do we want? We want 4 tangent squared theta plus 4. And so what is our substitution? X squared equals 4 tangent squared. In other words, x equals 2 tangent theta. And then our differential is 2 secant squared theta d theta. So this integral on the right now becomes, let's see, so our dx is going to be 2 secant squared theta d theta, and the denominator now, x squared, was 4 tangent squared plus 4. So all the techniques are kind of coming back here on us for this problem. Okay, so we finished one integral. That one's now easy. This one we got to do a little bit more work for. So what do we got? Natural log of x plus, this will just be 1/2 natural log of u minus, we've got 2 secant squared theta over, that's going to give me 4 secant squared theta. So all I did was factor out that 4 there, and then use that identity, d theta. So we've got natural log of absolute value of x plus 1/2 natural log. U was x squared plus 4 minus. So those two are canceling. 2 divided by 4 is just 1/2, and I've got an integral of d theta. So we'll just get a theta. And on this one, since it's generic integral, we can add that plus c. And of course, our last step is to solve for our theta. So what do we have? So we had this guy here was our substitution equation. Solving for theta, we'll just get arctan of x over 2. I showed you guys the trick yesterday of having to draw those triangles. Sometimes you have to draw a triangle, sometimes you don't. In this one, since we just have a theta there, it's easy enough to just solve for theta with arctan. So let's write out our final solution. Natural log of absolute value of x plus 1/2 natural log absolute value of x squared plus 4 minus 1/2 arctan of x over 2 plus a constant. So you'll see these functions a lot of natural logs, a lot of arctans in these solutions for partial fractions. Any questions on this guy? So I'll leave it up here for a second. Let me know if you're still writing or if you're all set.
Still writing.
Yeah, figured so. There was a lot there that I was kind of getting through at the end. So we've only got about 20 minutes left, and that problem itself took us like 20 minutes. Some of these problems, just writing out everything is a lot. So I don't know how you guys saw this on Calc 1, but in Calc 2, a lot of times what we do is we don't have you complete problems. Like we really want to see, do you know the partial fractions? So in these next couple of examples, let's just try to talk about the techniques, set up the partial fractions. Then like these last steps, once you get here, right, we've kind of reduced ourselves to previous techniques. So hopefully if you guys are practicing those as we've been kind of cooking through these summer semester and these days, hopefully these steps are starting to become easier and easier. So let's try to do a couple more and see what else might come up in these partial fractions problems, but then maybe stop like once we're able to break it down in the partial fractions and not finish these last few steps, just to see some more examples. All right, you guys all set? Everyone finished writing, or are you guys still writing?
Almost done.
Okay. Go ahead and take your time. And I will try to put all the course notes up. Did the Google Drive, all you guys have access to it? With the course notes? I don't know if you guys checked. I'll try to get those on the website. I think if I get in touch with Al's the course coordinator. And it might be kind of nice. Summer semesters are a little weird. It's like a coordinated course, but yet each of the instructors are kind of doing their own thing for quizzes and lectures, obviously. So I don't know, maybe on the course website, I'll try to see if I can get a specific page for my section and put my class notes and my lectures, or at least put links up to there. So that way you guys don't have to like dig through emails and find, where is the correct YouTube link? Where is the correct Google Drive link? It's at least all in one place, and then you can check the links from the website. And so you really only have to keep up with the website and Canvas. That should be enough.
All done.
All done? All right. So the two other situations that arise are sometimes the numerator. So what if the degree of the numerator is bigger than the degree of the denominator? So when we've done these partial fractions, let me pull up the page of notes when we did these. It really relies on the fact that because I have the denominator split, when we refind the common denominators, right, what degree of polynomial am I going to get on the right side? It's only the degree of the denominator. Because when we find these common factors, those will increase the degree. Right here, we had a degree 3 on the denominator. So it's actually going to be 1 less is the way we cooked it up. So what happens if the degree of the numerator, and I should say bigger than or equal to the degree of the denominator? This is one of those situations, hopefully we won't throw many problems like this at you, because it just adds another step, and we already see how long these problems take, and it's just like a computational pre-calc thing. So what do we have to do? We have to do long division first. Just another pain. So hopefully you guys won't have to do too many of these. Let's try to get through one real quick here in the last 20 minutes of class or so. So we've got x cubed minus 4x minus 10 over x squared minus x minus 6 dx. So this is kind of like something you might want to write as step 0. If you kind of wrote out those steps in your notes. What would come before step 1 would just be to check that the degree of the numerator is less than the degree of the denominator. If it is, go ahead and do the problems, denom. Go ahead and do the problems like we have been. If not, we got to add this step before doing the partial fractions. So I don't know how many of you guys remember polynomial long division from pre-calc. Might have been a little while ago since you've seen it. So let's go through it real quick. Let me rewrite it. So you put the numerator underneath. I'm going to write it as x cubed, and I'm going to put in a placeholder for the x squared term. X squared minus 4x minus 10. So we had 0x squared. And then we are dividing by x squared minus x minus 6. So you always compare the highest powers first, and then the rest kind of just follows suit. So we've got x squared into x cubed. What do we need to multiply that? We need to multiply x squared by x to get x cubed. Then I take this factor and multiply by everything here. So we will have x cubed minus x squared minus 6x is multiplying that factor times all of those guys. We then take that whole thing and subtract it from whatever is in the numerator there. So when I subtract it, the x cubes, the highest power should always cancel. I will have a plus x squared. Of course, you could have put that as a plus 0x squared. So we've got plus x squared. We'll have plus 6x minus 4x. So it'll give me a negative 2x minus 10. And now the degrees are still the same. So we've got one more step. I've got x squared going into 1x squared. So it's just plus a 1. So I take that 1, multiply it by that whole thing. So we'll have x squared minus x minus 6.
Sorry, this might be a dumb question, but why is it minus 2x?
Positive 2x. Sorry about that. Yeah, thanks for catching that.
Okay, cool.
Yeah, so because it's plus 6 minus 4. Yeah, okay, so we multiplied our 1 through, then we got to subtract, and of course the x squareds cancel. We will have a positive x plus 2x gives me a 3x, and then I'll have a positive 6 minus 10 gives me -4. So just a bunch of work there. This is now the new numerator. And notice that it's degree 1. So it's 1 less degree than what the original denominator was. And as you kind of saw, things to look out for, minus sign errors. It's hard to keep track of all these adding and subtracting things going on. Okay, so what's this say? This says our original integral was x cubed minus 4x minus 10 over x squared minus x minus 6. That's going to equal the integral. This is just a polynomial part. So it's going to be x plus 1. And then now plus 3x minus 4 divided by x squared minus x minus 6. So we took what we originally started with and basically reduced it now into an integral that we can easily do, and then now something we'll have to do partial fractions on. And this is where it gets, a little hairy just in terms of organization. So we can go ahead and integrate the easy part, and then we've got 3x minus 4 divided by, how do we factor x squared minus x minus 6? Hopefully that's popping out at you guys. X minus 3, x plus 2, and then now we just have to do partial fractions on this guy. So I'm going to keep this box and just remember to add it in my end of solution, since the rest of the work I want to write out, I don't want to have to keep writing that guy out. And so what are we going to have? We're going to have 3x minus 4, x minus 3, x plus 2. It's going to be a over x minus 3 plus b over x minus 2. So we will have 3x minus 4 equals a times x minus 2 plus b times x plus 2. I'm missing my minus signs again. B times x minus 3. And nicely enough, these are linear factors, so we can just check values. So let's do that over here. So we'll check x equals -2. What's that going to give us? On the left, 3 times -2 minus 4 is equal to, if x is -2, this term is going to go away. I'm not even going to write it. B times -2 minus 3. So that's going to give me -6 minus 4 gives me -10 equals b times -5. So b equals 2. And then our other factor, let's check x equals 3. So we will have 3 times 3 minus 4 on the left. And then that term's going to be 0. So we will have a times 3 plus 2. So distributing, we've got 9 minus 4. 5 is equal to 5a. And we get a equals 1. You guys still writing?
Yeah.
Okay. So again, if you're kind of a little hesitant on this step, just take a look at, go back through the work, go back through your notes, after class, double check how we did the first problem where I wrote out every single step, first and second problem, and then try to fill in the steps of how I got from here to here if that's still bugging you. Let's see, what page are we at? Page 7 in our notes. Still writing?
Good.
Good. All right. So let's go ahead and finish off what we had. So just the partial fractions part. We are turning this integral, 3x minus 4 over x minus 3 plus 2, now becomes an integral of, let's see, so my a was 1. Oops. My a was 1, and that was over the x minus 3, and b was 2, and that was over the x plus 2 dx. Oops, sorry, that wasn't on the video there. So this is just our partial fraction decomposition. My a was over x minus 3, b over x plus 2. And that integral is easy enough. So what's that going to be? Natural log of x minus 3 plus natural log of x plus 2. And that one had a coefficient of 2 out front plus a constant. So that's just the partial fractions. The full solution. Let's just remember that polynomial part that we found at the beginning. We had 1/2 x squared plus x plus natural log of x minus 3 now plus 2 natural log of x plus 2 plus a constant. Okay, so that's basically all of it. There's one extra thing that can occur when we have the factors of the denominator with multiplicity bigger than or equal to 2. So let's not even set up an integral. Let's just play around with the partial fractions part. Excuse me. So what do we have? Let's say I have something like 3x plus 4 over x plus 1, x minus 2 squared. So this isn't necessary, but it's possible. So how do we break this down into our partial fractions? We are going to have an x plus 1, but this term here, it's a linear factor. It's just of degree 2. That's what we mean by multiplicity 2 or more. Sometimes this happens. What you can actually do is write it like this. So instead, what we could have done, we could have just ignored this b or ignored this x minus 2 as like a linear factor and just had it as the way we should have done. So let me write an or here. Oops, x plus 2 squared on the outside. So if we were to do this problem the way we've done all the other ones, since the denominator is a squared term, I would need a generic polynomial of degree 1. So bx plus c in the numerator. This is how we've been doing it. But if you don't want to deal with like this bx plus c term, there's another solution where you can set up your constants like this. So since I have a degree 2 multiplicity, I can essentially just write it as one factor, x minus 2, with a constant. And then now, even though this one's squared, I can keep this guy as constant in the numerator. We don't have to deal with like a cx plus d here. In some sense, they are equivalent, and I don't have much time to explain why since class is about to end here. So if you want, try to think about why, right? The key thing comes down to if I wanted to combine these two into one expression, I would have to multiply this one by x minus 2 over itself, which would give me that b times x minus 2, or that bx term, which would take care of, in some sense, this linear factor, or give us an equivalent way of solving it. The nice thing about this really is just the fact that we don't have to have these bx or anything like that. It's all just constants in the numerator. Likewise, if I have something like, I don't know, so let's make up a numerator. Let's just keep the numerator as a constant. Let's say it's 12. And the denominator is something like x plus 1 times x minus 2 cubed. If you want to break this down into partial fractions, you could write it as a over x plus 1 plus b over x minus 2 plus c over x minus 2, squared plus d over x minus 2 cubed is one way you could do that. The other way, following our standard method that we've been doing, I would write it as a over x plus 1 plus, well, now our denominator is a degree 3 denominator. So this is the only time when we can get a degree 3 or higher, is if it's a factor with a higher multiplicity. So then you would have to write it as a degree 2 polynomial in the numerator, bx squared plus cx plus d. And we could go through our standard method of finding the common denominator and equating the numerators to find all those constants. Now, just as a fair warning, when I write this or, these constants here are not the same. So maybe we change them. The a's will be the same, but let's call this b prime and c prime. And this one, b prime, c prime, and d prime. You will get different constants. These constants don't match up, but they will ultimately give us the same answer through some algebraic manipulation. If I go from this factored form to this factored form, we will get the equivalent expressions. Any questions on that? Again, those cases, they don't come up a lot, and I don't know if you'll ever really see a cubic one just because it is a lot of work. And the ones, I mean, you've seen how long these problems can take. You know, we can't throw stuff like that at you too often, especially with timed exams and timed quizzes and everything like that. So you might see something like that on a homework, and really it would be at most maybe a degree 2, just to see if we can check your understanding of how to solve something like that with a multiplicity, with a root multiplicity of 2 or more. Any questions? All right, so I'm going to go ahead and stop the video.